Hello again. We are starting a new chapter on stochastic convergence and limit theorems. So far we have learned about random variables, a pair of random variables, a vector of random variables, and then we extended these to a sequence of random variables. So we could work with a sequence of random variables, let's say x1, x2, xn, and etc. So you remember when you had a sequence of real numbers, we had defined in your calculus from your undergraduate the concept of convergence, the concept of limit. Now we have a random variable which is not a real number, and therefore these entities, they are extended. So the concept of convergence needs to be extended as well. And this is what we are going to do in this chapter. So this chapter is a little bit more theoretical, and it is meant for your exposure. So if you need in your research or work, you can learn by yourself a little bit more. So in this chapter, we will learn different definitions which for the convergence, and a random sequence x and etc. could converge into something, some random entity, by some definition, and it could diverge in some other definitions. So we will learn about different mode of convergence. We'll define different type of convergences, which some of them are stronger than the other one, and some of them they are weaker, and then some of them they may be apart from each other. Then we'll learn necessary and sufficient condition for some of these convergences, and so on. Once we learn those, we learn about law of large numbers, and specifically we give an example of central limit theorem. In this theoretical chapter, we'll introduce basic different possible notations for convergence, which relates to how a random sequence or random process can sometimes be expected to settle down into a behavior. For instance, the mean of a random sequence may, after time goes by, becomes constant. In that way, in that case, we say the random process is converging in the mean sense. For example, if a random sequence eventually behaves like a constant value in some sense. So the sense, or because we are dealing with random entities, so we have to make a measurement of that randomness in order to define the senses. Or if a random sequence continues to change, but some statistics of its probability distribution settle down into an unchanging behavior. For instance, after time goes by, your random sequence behaves like a normally distributed random variable with a given mean and some given variance. Then in that case, we say that the random sequence converges to a normal distribution. So its distributions converges to some random variable. So a stochastic convergence of a random variable could have several different meanings. So first, a random sequence or a discrete time random process is a sequence of random variables. We here present only the main type of convergence of random sequences. So sometimes we abbreviate these as a random sequence, and here n varies from 1 to infinity. So we have different type of convergences because a random sequence is a function of random outcome, and for some of these possible outcomes you will have convergence, for some of them you won't. So what we can do and what we should do.